Okay, so let's take a moment now to retrace our trajectory. We started out by arguing that the safest possible theory is one that makes the fewest number of assumptions possible. We then proposed one such model built from only directed algebraic graphs. That is, we do away with any additional notion of an underlying spacetime. Now, when the algebra is chosen to be the complex quaternions, then we find that we can describe each of the Lorentz representations of the standard model in a concise way. These Lorentz representations are defined by the behavior under the discrete symmetries of the algebra. Okay, so now we want to scale this up. And when counting all of the off-shell degrees of freedom of the standard model, we find that we need a space that is roughly 250 real degrees of freedom. As it turns out, we can find a relevant 256 real dimensional space by taking a certain real slice of RCHO's left multiplication algebra. This CL08 slice is especially interesting for us because it is ubiquitous in the world of real Clifford algebras. Furthermore, it might just supply us with a natural incarnation of a Fock space. So now we're at the point where we need to describe how the standard model's degrees of freedom can be embedded inside this CL08. Now, for practical reasons, we're going to do this by first analyzing its structure at the complexified CL8 level, and then we're going to restrict down to this real CL08 slice. Now, it's crucial to note that we're not dealing simply with CL08. So CL08 on its own is nearly a featureless box. Instead, we are using a special version of CL8 that is generated by the algebra RCHO left multiplying itself. That is, we will obtain CL8 from the left multiplication algebra of RCHO. Now, these division algebras are, of course, also examples of recurring structures that pop up over and over again in various branches of mathematics. Now, specifically, here are the 8 generators that we are going to be using for the CL08. The L here refers to the left multiplication algebra. The E's are octonionic imaginary units. The epsilons are quaternionic imaginary units. And the I, of course, is the usual complex imaginary unit. So at the end of the day, what we have here is real CL08 with extra division algebraic substructure. And it's this division algebraic substructure that is going to help us break CL08 down. So in our first step, we're going to bring to light some important substructure that comes to us from the octonions. Now, as many people will know, the left multiplication algebra of the octonions is given by CL06. Furthermore, you may know that it's possible to describe the volume element of this Clifford algebra by a single octonionic imaginary unit. For concreteness, we're going to call this imaginary unit E7, but of course, there's an entire 6 sphere of candidates that we can choose for this imaginary unit. So this octonionic substructure is going to single out for us a volume element that is expressed as an octonionic imaginary unit. Now, with this octonionic imaginary unit E7, we can construct projection operators that we're going to call little s and little s star. Now, these projection operators may be viewed as generalizations of chirality projectors familiar to you from the Dirac algebra. Now, the octonions have this peculiar property that any octonion multiplying from the right can always be rewritten as chains of octonions multiplying from the left. And so this means that with this same octonionic imaginary unit, E7, it's going to give us a second pair of projection operators that we're going to call capital S and capital S star. Here, the R refers to right multiplication on CHO. So the octonionic substructure of our complex CL8 gives us 2 sets of commuting projection operators. Well, what are these octonionic projection operators going to do for us? Well, they're going to take our complex CL8 and they're going to partition it into blocks. Now, there's one very curious feature about these blocks. These blocks are of various different sizes, and these sizes happen to fit the Standard Model's particle representations rather closely. Incidentally, this partitioning is an example of what's known as a purse decomposition, and these purse idempotents will correspond to projective measurements in our model.